Good morning. Welcome to this lecture. My name is Alessandro Golcar. I'm an assistant professor at the Skolkovo Institute of Science and Technology. And this morning I would like to talk about this lecture on what is system architecture and why it's important for the development of complex engineering systems in space. Well, first of all, a little bit words about my background. I work in Russia. My group is called Strategic Innovation Research Group, and we do primarily work in system engineering and development of complex space systems, both on the conceptual stage and at the hardware level. We do a little bit of stratospheric balloon flights with experiments that come from institutes, research centers in the Skolkovo Institute, Skoltech. So, this talk is divided in two parts. Part one is going to talk about system architecture, and part two is going to talk about some tools that you can use to do system architecture. In this part, what I would like to do is to talk about systems thinking and its relevance to the design of complex engineering systems. I would like to talk about the concept of emergence, what it means, and basically what I will show is that the main reason why we do a system is basically to have emergence, because the final function that the system delivers, or the functions that the system delivers, are greater than what it just gets from the individual parts alone. Okay, and this is what emergence is. Unfortunately, to get emergence, you have to work with complexity, right? So every time you develop a new system, there's going to be complexity associated with it, and we're going to talk about how can you manage complexity, or in better words, how to understand complexity in your design. Finally, in this part, I'm going to talk about what is architecture, what is function, what is form, and what are interfaces for a system. So first of all, I would like to distinguish what is architecture and what is engineering. There is a very nice book that was written by Rektin on the art of system architecture, in which he discusses the difference. And he says that, I'm just quoting from his book, he says that generally speaking, engineering deals almost entirely with measurables using analytical tools that are derived from mathematics and the hard sciences. So engineering is really an analytic discipline, okay? And it's a deductive process where you're starting from principles that are scientifically derived and proven. Then you can do your whole work and analysis, etc. On the other hand, architecture, while it has connections, of course, with engineering, it is very different. Why? Because it deals, as Rektin says in his words, it deals largely with unmeasurables using non-quantitative tools and guidelines based on practical lessons learned. So whereas engineering is a deductive process, architecting is an inductive process. In a sense, engineering is more of a science, right? And architecture is more of an art. And what this talk is about is architecture. So how do you go about when you have to design a new system from scratch, right? And you have to deal with the creative part, right? So for example, when you're designing a car, the two types of work, for architecture would be to understand that the car has, for example, 4 doors, 4 wheels, that it's got this type of traction, rear traction, for example, etc. In the design part, in the engineering part, is where you analyze, for example, the thermodynamic performance of the engine, or the aerodynamic performance of the car, the vehicle, and so forth. So as you can see, those two concepts are intimately related, because in the engineering part, you have to have an architecture to start. You have to have a design. In the architecture part, there is not so much quantitative analysis just yet, but you have to come up with the whole concept to be analyzed. So it's really, really important work. So let's first of all give a formal definition of what I mean by system. This is something that people have different definitions depending on the field where they come from, and what I'm going to give you now is just one possible definition. There are 1,000 of them in books. So possible definition is that a system is a construct or collection of different elements, which together, when you put them together, they produce results that are not obtainable by the elements alone. This is the whole point of doing a system, right? So collecting elements so that the final function is better than, well, it's new and it's what you need to satisfy your needs. The elements of the system, they're not just technical parts. So typically engineers think at systems in terms of only technical elements. For example, I don't know, going back to the car example, you know, the doors, seats, engines, so far and so forth. But in reality, you know, in addition to that, there is the whole other components, for example, people. You know, you cannot design a car if you do not understand people needs, right? So that they need to sit, that they need to be comfortable, that they need to look at the road, and things like that. You're also looking at things like, you know, well, of course, hardware and software, but also facilities where to integrate and test this hardware and software. Policies, right? So regulations are very important because otherwise you're not able to make your system commercial. For example, you cannot market it if it does not comply with policies and regulations. And finally, documentation is a part of the system, right? Results of, you know, system work, so basically developing systems, they include, of this analysis include qualities that you want to get out of the system, properties, some characteristics, functions that you want out of it, behavior and performance. And in a sense, we may say that when you develop a system, what you're trying to do is to add value. And the value added by the system as a whole is what you get out from the interconnection of the parts. So let's say the magical place, you know, the place where magic occurs is really those interconnections, what I call the interfaces. So the reason why a system is, you know, able to create new performance and new functions is because interconnection makes, you know, possible to create something new. And this new is what I call emergence, okay? So I would like to stress again from the definition I gave previously, when I said elements that together produce results that are not obtainable by the elements alone, that's what I call emergence. So, you know, for example, an example of emergence, if you take, for example, a telecommunication satellite, going back to space, you know, the reason why you do a satellite is not to build the satellite itself, right? The real reason why you do the satellite, let's say the emergent property that comes out from the development activity, is the ability, for example, to entertain people that watch television channels that are broadcasted by satellite. So this is the whole point, you know, that there is, for example, a satellite TV industry, right, to entertain. So this is the emergent property. Now, of course, this type of emergence, you can figure it out, is everywhere. It's, you know, in any aerospace project, for example, if you think at rover missions, emergence is probably going to be on the science side. If you think at, I don't know, UAVs, probably they're going to be useful to satisfy some agriculture needs, for example, in land monitoring, and so forth. We said before that emergence is the reason why we do systems, right? We want emergence to occur in the way we predict and that we want. Now, the problem with that, let's say the other side of the coin, is complexity. So to get, let's say, very high performant emergent functions, you have to pay in complexity. So, for example, to design a satellite system is not easy, right? So there is a lot of complexity. The telecommunication satellite is a complex system to build, and especially in modern systems, there is no single person who has all the skills and knowledge required to build a whole, you know, spacecraft, right? This is the whole point of, you know, having complexity that we need to manage, understand, and you know, deal with it in a way or the other. So As an example of complexity, consider the first flyer that was available, the first plane that was developed, the Wright Flyer, right? So that airplane was, very a marvelous invention and really a breakthrough in our society. But the way it was developed, the architecture that was underlying this airplane had limitations, right? So as you probably know, and as you can see in this picture, the pilot had to lie, right, horizontal in the plane. The plane has this so-called canard configuration where the stabilizing surfaces were on the front, and the airplane was made of wood and paper basically, and with very low power engine. Of course, it was not possible to scale up this system, right? So that the architecture of this system had its own limitations. Why? Because complexity, when you were trying to scale it up, grew dramatically up, right? So it was not possible to have, for example, having that architecture, the emergent function of flying was only possible for one pilot, definitely not for example, 100 passengers, right? So, okay. And complexity also happens, in every project that is in human society for technology. If you think at, planetary rovers again, UAVs, they are very complex systems that need to be, in which several people work. Project like this can involve the work of 100 people or more, and those people have to be coordinated in a way so that these very complex systems at the end of the day will come up, right? Because it's very hard to have otherwise the combination of all the elements work in a seamless way. What approaches do we have to manage complexity? Well, there are basically three approaches, if you think about it. There is decomposition, abstraction, and hierarchies. Decomposition means that you can take a system and decompose it in two parts, right? So if you take, for example, an airplane, you could decompose it, in wings, fuselage, stabilizers, and so forth. If you take a spacecraft, you can define, the power subsystem, structure, thermal, propulsion, and so far and so forth. So this is what I call decomposition. And basically what you're trying to do is to decompose the system in its atomic parts that are more manageable, easier to understand, and then can also be worked on by sub-teams of your development group. Very coupled to the decomposition concept is the hierarchy concept. So when you do hierarchy, basically you're starting to put layers, and you're starting to say that there is a main system that is composed into components, which of course are in a lower level of the hierarchy, and maybe these components are made themselves by parts, and so far and so forth. This is a way to structure a decomposition in a way to understand this complexity. And also abstractions, right? So sometimes what engineers do, they abstract some elements in their functional attributes, right? So instead of looking, for example, at the specificities of an attitude control system, what they know is that, for certain analysis, this can be treated as a black box which provides some attitude control function, right, which can be modeled in an abstract way. So let's talk more about these three very important concepts. Well, for example, if you think at abstraction, there is a colleague at Crowley who defined abstraction as an expression of quality that goes apart from the object and has only the intrinsic nature rather than the form. So when I say function, I say let's say that the thing that the system does, right, without talking on how it does it, what is the hardware implementation. So for example, for a pen, the function is to write, right? So you can write in many different ways, and a pen is just only one of them. And in abstraction, this is what you do, right? So you detach yourself from the physical embodiment, and you only look at the action, the actual function that's being delivered, which is the real reason why you want to do, you want to have a pen, for example. You can use abstraction not just in from what they call form, so the hardware form, but you can also use it on the functional level. So if you have a very complex function, you can abstract into, let's say, component functions. Let's take, for example, an Earth observation mission. As you probably know, Europe, for example, is very strong in Earth observation. So when you do a mission, what does it mean? Well, an abstraction, to understand what it means, is that you have a launch segment, so you have a launch vehicle that brings the satellite up there. You have a space segment, so the satellite itself, and the ground segment, which is the ground station that tracks the satellite. And of course, the space segment, you can use decomposition, which we're going to talk about later, and hierarchy and abstraction to understand it better. So this is to say, it's a way to understand a very complex system in a very simple, let's say, compact way. Also for hierarchy, I would like to use Crowley's definition, in which he says that a hierarchy is a system in which grades or classes are ranked one above the other, right? So there is an inherent ranking of things that helps you to understand what is complexity and how to manage it. It's a way to focus yourself on the things that really matter to you as a designer. So for example, if you're a thermal engineer, you don't need to know the details of the electronics of your spacecraft, right? You just need to know, for example, that the heat being produced, materials, for example, that are used, and so far and so forth. So for you, only having that information and forgetting about the lower hierarchy details, well, that's useful to you to focus on what you need. And third is to give a structure to the description of the system. So hierarchy allows you to get a system and basically put things in order in a way that is understandable to you. Let's talk finally about decomposition. So decomposition, again adopting Crowley's definition, is the division of a system into smaller constituents, right? And as an example, well, everybody knows in the satellite world how to decompose a satellite, right? So you have a payload, you have thermal subsystem, structure, a DCS, and so far and so forth. So this is how you do decomposition. Now, what is the difference between hierarchy and decomposition? Well, it's quite subtle, right? So in decomposition, basically you're identifying the elements and you're trying to get a whole and make it into constituents. In hierarchy, you're trying to organize those elements in a rational way. How many decompositions and hierarchies you can define for a system? Well, typically people think that there is only one way to do it, right? So if you think at a satellite, everybody would gonna say power, thermal, structure, and so far and so forth. That's not necessarily the only way in which you can decompose a system, for sure, or the only way in which you can rationalize a hierarchy. So in system engineering, what people do is actually devise the hierarchy and decomposition that makes the most sense for that particular occasion. So this is what is really important to understand. That there's not only one way to do hierarchy or decomposition. There are several ways to do it. And how to do it, well, it's an art. And there are systematic tools on how to do it. And this could be the subject of an individual lecture per se, on how to, devise hierarchies for some specific scopes. Now, we talked previously, we introduced the idea of systems thinking, right? So if you have to think of the system, what does it mean? As we said before, the definition of a system is not only about the hardware, it's not only about the software, but there is also people, there is facilities, policies, documentation, and so forth. So systems thinking is about, considers not only the technology aspects of a development, but also the business and policy. Right? So if, for example, if you're a commercial venture, let's say you're a new space company, what is important to you is not just performance, but also the profitability and the sustainability of your venture, to mention two important aspects. But also, for example, policy compliance. Right? So whatever you develop has to have compliance with the policies of where you intend to operate. Right? So for example, bandwidth allocation, just to name one. For communications. Now, of course, if you think about it, this impacts all major aerospace projects. So if you take, for example, making reference to planetary rovers, they typically have instruments that come from different countries. So to devise, for example, having the decision to have a joint development between countries for a planetary exploration system has very deep impact on the technical realization. Why? Well, consider, for example, the previous incarnation of the ExoMars program, which was an American-European development program. Well, of course, whenever this happens, there's going to be the influence of ITAR, export regulations in the United States, similar regulations in Europe, which means, for example, if you don't divide the work well, properly, you're going to have a lot of schedule slips and cost growth, just because the policy works in a way that this technical division of work does not work, right, for that program, right? And for example, the same similar issues you have in UAVs. So there are, for example, export restrictions on UAVs for certain applications, and when you develop, if you want to start a company that works in that area, you have to consider all these aspects, right? As part of the design. It's part of the design of the architecture. I would like to give some principles. Architecture, as I said, is a heuristic art, and so it's not something that it's easy to learn on textbooks. I teach a course in system architecture in my university in Skoltech, and what I tell to my students is that what I teach them is just an introduction. Really, the way to learn architecture is by doing architectural work in the field. It's a heuristic art. It's like painting or this type of creative art forms. I can share with you some lessons learned, and there's a way to identify some patterns, things that typically are good in any type of work that you do. There are great books about heuristics on system architecture. I mentioned before, the Art of System Architecture by Rechtin, but I'm also thinking, for example, the famous book by Norm Augustin on the Augustin laws, in which he postulates, heuristics based on several, 30, 40 years of work in the aerospace industry, in which he talks about business, for example. Now, I'm going to share with you 3 of my own principles. Your job, if you want to be a system architect in your career, would be to come up with your principles, okay? My 3 principles, which, are not really, let's say, novel, but these are the ones that I adopt. First one is elegance, second one is traceability, and the third one is what I called Occam's razor. So elegance in system architecture means to find the simplest solution to complex problems. So sometimes people confuse simplicity with something easy, but it's not like this. To reach a simple solution for a complex problem is actually the hardest task that you can take. For example, thinking of commercial developments, one of the reasons why Apple was successful with its iPod, when it was first introduced, is that it made simple the whole process of purchasing music and bringing it with you on a very simple platform which had a sliding wheel, and that's it, right? So it's very simple interfaces, very simple streamlined way to purchase music and so forth, and this simplicity brought them to success, right? And simplicity can be designed upfront. So it goes, let's say, beyond the engineering side. It goes into the architecture side of things. So simplicity relies in architecture. Now, this is not a linear process. So it does not mean that to design simplicity in an architecture, you can start, let's say, from step 1 and then go step 2, step 3, step 4. It does not work this way. Sometimes you have to start from architecture, go into engineering, realize that what you've done does not really make sense on the engineering side, or maybe from the engineering side you realize that there are simpler ways to do what you're intending to do, and you go back to the architecture table. So this is really an iterative process which goes between architecture and engineering, right? And eventually will lead you to a result, right? The there is this famous 80-20 rule that says that it's very important to invest in this process early in the design stage, because the decisions that you're going to make in the architecture side, once you fix them, they're going to have tremendous impacts, right, on your production line, on your system, on everything you do. And to change them later on in the design, or let's say if you're at production stage or if you're operational, it's going to be very expensive, and sometimes it's also not impossible to do. A caveat that I want to give is that to do simplicity takes work. Typically, when you have a new problem, what it comes in mind to you first are the complex solutions, and these are the ones you have to prune out and go back to the drawing table and come up with new ones. So teamwork in this type of early process is essential, because it allows you to come to simple solutions in an easier way, faster way, to do it in teamwork. Again, I want to stress, do not confuse simple with trivial. There are very two different things. It's like to say that the system is complex or the system is complicated. Of course, all the systems are complicated in the sense that they involve a large number of things to consider, but complex means that the outcome of that system, the results that you get are the result of nonlinear interactions of components, and so they're hard to predict. Very different concepts. So likewise here, simple is very different from saying it's trivial. Elegance typically implies that you're able to minimize the operating functions that you need to deliver whatever emergent behavior you need. You are able to minimize the number of elements that you need, which in other words means to minimize complexity. It means to minimize the number of interfaces. As I said before, between the different elements of a system, there is always an interface, be it mechanical, fluidic, electronic, informational, whatever that is. Complexity comes out from the interfaces, right? And system engineering is really about managing those interfaces. Minimizing them is a good idea if you can. While still, everything I said, while still satisfying stakeholder needs. So there are some needs to be satisfied. This is why we as engineers and system architects, we design a system and we design a system architecture. So we cannot compromise on that, except if you do some work, which we're going to talk in part 2 of this presentation. You can also, let's say, trade needs, right? So especially if people don't know exactly what they want. So this was about elegance, and now I would like to talk about traceability. Traceability is a very important concept that is stressed in many different sub-disciplines of system engineering, and it means that whatever function that you embed in your system, it must be traceable, it must be reconduced to a specific stakeholder need. You have to have a one-to-one mapping between functions and needs, because otherwise you are introducing in the system things that are not really required, right? And to do that, you have to focus on what I call the value associated operands. Okay, so for example, for a satellite system, okay, telecommunication system, the value related operand is the data, right? The data that you produce, that you transmit, broadcast. This is really the reason, is the object for which you build the whole enterprise, right? And it's the object that adds value to your enterprise, right? So you don't design a satellite because you want to have a fantastic attitude control system. You design a satellite because you want to have data out of it, right? Or broadcast data. So focus on that, build functions around that, and make sure that all those functions are traceable to the needs given by the stakeholders. For example, in the example of data, if you want to have low latency in your system, let's say satellite constellation, make sure that this low latency is really reconducible to a need that has been elicited by a stakeholder, which needs data with low latency. Otherwise, it's an unnecessary requirement, which is may drive your costs up, may drive your schedule, to go longer than expected, and so far and so forth. And really, you have to do this mapping. It's very important, especially in complex systems, because sometimes, when work is done by hundreds of people, you may have the situation in which some people use functions maybe for previous experience, maybe for personal biases, but they're not really required at the end. A third and last principle I would like to share with you is the idea of the Occam's razor. So this is reconduced to a Franciscan friar that lived in the 13th century, 13th, 14th century, and was a scholastic philosopher. And in Latin it said, well, I'm going to give you first the Latin expression and then the English one. It says pluralitas non exponenda sine necessitate, which means do not include plurality if it is not necessary. So in system architecture terms, this means that, again, good concepts are simple, lean, and elegant. Do not add complexity if you don't really need to. This is what Occam's razor is about. It's to use this razor to take off the unnecessary parts. I would like just to summarize what we've been talking in this part one. So we talked about systems thinking and why it's relevant to the design of complex engineering systems and infrastructures. And what I really cared about here is the concept of emergence and complexity. So what is emergence? Well, it's the reason why we do system architecture. And what is complexity? It's really the price that we pay for having that emergent behavior happening. And we just commented a little bit about architecture, what it is, what is functions, what are forms, what are interfaces, and what are relevant. And in particular, that most of the magic of system engineering happens at interfaces.